recording, share the screen. Okay. All right, so we're over here. I'll do a little bit more of 1.3 and go on to 1.4, it looks like. Here's what's happening. So knock off a little bit more of 1.3, start 1.4. Reminder, by the time of the first exam, you submit all of this, okay? So when's our first test? It's Friday, just before Labor Day weekend, so I thought that's a good time to have it. So it's not this coming Friday, but the Friday after our first exam. So coverage is all of chapter 1. This is what you turn in. You must turn in at least 70%. I mean, ideally, you turn it all in, of course. You must turn in at least 70%, but truth be told, I end up doing what, 30%, 40%, and 50% of it anyway. So you've already got that down. All you have to do is submit the rest. Okay, you're allowed one cheat sheet, paper like this, 8.5 by 11, both sides. You can write anything you want. Okay, good deal for exams. And then, so on the exam day, just take a picture on your cell phone of your test and also your homework, and that's what's going to happen. Okay. All right, so let's get back to where we were. I was going to do problem 47 and 61 as leftovers. Okay, ignore this. So we're doing 1.3. Okay, so 47. Okay, sketch the region in the xy plane. X squared plus y squared greater than or equal to 4, and y is less than or equal to x. Okay, and sorry, you can't see it there. I've got it over here. All right. So x squared plus y squared less than or equal to 4. Y is greater than or equal to x. Okay, so x squared plus y squared equals 4. Okay, so you should know that if it says x squared plus y squared equals whatever, that's a circle with a center at the origin. Okay, so they don't have any like x minus 3 or y plus 2 or something like that. If it's just x squared plus y squared equals 4, that's a circle, center of the origin. The radius would be 2. Okay, so the radius is 2. Less than or equal to means everything inside of it, less than that. Okay, so ignore everything I have right now. I have a circle, center of the origin. It's a closed circle because of the line underneath it. Now, if you did not have that line underneath it, like pretend it was just like that, I would have a dotted circle. That's kind of like the dotted line, right? So this is going to be a closed circle. And then since it says less than, that would be shading inside. If it said greater than, you'd be shading all the outside stuff. Okay, so for now, I have everything inside the circle. But on top of that, it says y is greater than or equal to x. Okay, so y greater than or equal to x. Y equals x is a line, slope of 1. Think of y equals mx plus b. And the y-intercept is the origin. Okay, so it touches the origin, goes up at a slope of 1, and it's a solid line because I have the line underneath it. If I didn't have it, it would be a dotted line. Okay, so I have this line right here. Okay. And then do I shade above or below? Well, greater than means above. So I shade, notice I shaded above. If it said less than or equal to, I would shade below. Okay. And we're joining with the word and. So I need everything inside the circle, but above the line. Okay, so think about it. It's got to be inside the circle, but above that line. So that leads me to this semicircular region right over here. So this is my final answer that I've shaded right here. Okay, so think of this semicircle curved here and straight across, and it's solid, including all the boundary, because I have the line underneath here, a line underneath here. If I didn't have the line underneath it, then they'd be dotted. Okay. All right, so that's that. And then the only other one I wanted to show you was 61, and then I was going to be done with the section. Okay. So 61, find the area of the region that lies outside the circle x squared plus y squared equals 1, inside the circle x squared plus y squared equals 9. Area formulas on the back inside cover. I'll give that to you in a second. Okay. Think to yourself, x squared plus y squared equals 1. What's the radius of that circle? It'd be 1, the square root of this number. Okay. X squared plus y squared equals 9. What do you think is the radius of that circle? It's 3. It's the square root of that number. Okay. So you want the area outside of this. This happens to be the unit circle. Do you recall the unit circle from trig? Okay. Center at the origin, radius of 1. This one has a radius of 3. Okay. So now here's the picture. All right. So very crudely, I have a circle of radius 1, circle of radius 3. So it's got to be outside of the small circle, but inside this circle. Okay. So it's kind of like a donut, although a two-dimensional donut, as it were, right? You carve out a hole in there. So they're asking for the area of the shaded region. Okay, so the formula for the area of a circle, you might recall, is pi r squared. Okay, so area of a circle was pi r squared. You may write that in your formula sheet on your cheat sheet in preparation for the test a week from Friday. So if I want the area of the shaded region, I just take the area of the bigger circle minus the area of the smaller circle, right? I'm just taking this total area and throwing this out. So I call it pi big R squared minus pi little r squared. Pi big R squared minus pi little r squared. Okay, so the bigger r was 3, the smaller r was 1. So pi times 3 squared minus pi times 1 squared. Okay, so that's 9 pi minus pi. And it looks like the final answer is just 8 pi. And just leave your answer as 8 pi. You don't have to punch it in your calculator for 3.14 and all that kind of stuff. Okay, just leave it as 8 pi. All right, so that's as much as I was willing to do from 1.3. So again, if you look at the list, I did a whole bunch of them. I did a whole bunch here. Okay, so I'll get started with 1.4. So again, my lecture pretty much is just shortening your assignment list. I just end up doing a whole bunch of stuff from here, right? Okay, so I'm going to get started with 1.4. So according to the calendar, sort of right on schedule, 1.3 and start 1.4. Okay, so 1.4, there are some rules to talk about. So let me go over them. And let me show you the pictures for that again. So if you never want to buy the book, I've got that. So 1.4, let's see, we're supposed to do 1 through 8 and 9 to 49. I got to show you at least to 49. Okay, so I'll try to make it as, you know, it's not that clear. So it looks like I'm on page 28 now, please. Okay, I'll try different angles. Again. So there's the top of it. And a little bit further down. I'll keep adjusting because sometimes when I adjust it, the angle gets better. And a little bit more. Okay, and just to be safe, I'll kind of sweep back through that again. Okay, and then in the other page, we had to go up to what? 49. Okay, so I guess up to here. So see if you can, I'm going to try to change the angle, try to find the best viewing. Almost feels like I'm going to the eye doctors when I do this. But it's kind of good there, although it's kind of crooked. All right, so there we go. Okay, so in this section, we're doing something called symmetry, symmetry of a graph. Okay, so you need to know the rules of symmetry. If you're following along the text, it's on page 25. Obviously, those of you that have the book, just look at your book. It's the best. Okay, so for those of you that I said you never have to buy the book, you are disadvantaged because you don't get any nice copy, I guess. Right? So rules of symmetry. You can put this on your cheat sheet again if you wish at the bottom. Okay, so we have y-axis symmetry. And by the way, I'll give you my version of it also. A graph has y-axis symmetry if negative xy is on the graph whenever x comma y is also on the graph. Okay. Y-axis symmetry if negative x comma y is on the graph whenever x comma y is on the graph. And then we have something called x-axis symmetry. If x comma negative y is on the graph whenever x comma y is on the graph. Let me adjust this a little bit, see if I can get it better. Not sure if I can. Whoops, seems to have gone yellow on me. The graph has x-axis symmetry if x comma negative y is on the graph whenever x comma y is on the graph. Okay. If you didn't get it all, that's okay. You can look at the video later, and I'll give you my version of it also. Now, what I'm about to show you is the wording is a little bit different, but it's equivalent. Okay. And then on the next page, 26, you have something called origin symmetry. For origin symmetry, if negative x, negative y is on the graph whenever x comma y is on the graph. Basically, you change the signs of both x and y. Okay, negative x, negative y is on the graph whenever x comma y is on the graph. Okay, here's a picture of something that has origin symmetry. If you take any point in a graph and reflect across the origin, you get a corresponding point here. And let's say this point here, which looks like a high point, ends up being a low point over here. And this point over here comes and reflects over here, and so on. Okay. So that's called origin symmetry. Top of 26, here's a graph that exhibits y-axis symmetry, symmetry with respect to the y-axis. So any point xy has a corresponding point negative xy. Okay. So you notice if I put a mirror here, right? You got a mirror image. Okay, this side is a reflection of that side. And here's an example of something called x-axis symmetry. Sorry about it changing yellow. I don't know why it does that. Okay. So anytime you have x comma y, you also have x comma negative y. And so you have x-axis symmetry. Okay, so notice it's like a mirror image here. If you put a mirror right here, the reflection of the top is the bottom and vice versa. So that's something called x-axis symmetry. All right, and now I'm going to give you my version. Okay, again, sorry, to save time, I have to have a certain amount of speed, knowing that you can always look at the video and the book. Okay, so here's my version of it. It's equivalent, 1.4, symmetry, and I have some examples. Okay, here's an example of y-axis symmetry. Y equals x squared. Okay, y equals x squared. It has y-axis symmetry. If I put a mirror right there, there's a reflection. Okay. Now, for this function, for this graph, what do you get when you plug in 2? Well, you get 4. But what do you get when you plug in negative 2? You also get 4. And that's always going to happen for this relationship here, right? If I plug in any number and I put the opposite of the number, you're always going to get the same thing. So that's called y-axis symmetry. Okay. If I just turn it around to x equals y squared, it has x-axis symmetry. So now, x-axis symmetry, right? If I put a mirror right there along the x-axis, you have a mirror image. Okay. And notice this time I have 4, 2, 4, negative 2, right? So if I replace y with negative y, I get the same thing. Okay. So if I plug in 2 right here for y, x is 4. But if I plug in negative 2, I still get 4. And y equals x cubed, that's something called origin symmetry. Meaning, what do you get when you plug in 2? 2 cubed is 8. What do you get when you plug in negative 2? Negative 2 cubed is negative 8. So you get the exact opposite. So that's something called origin symmetry. The point 2, 8 reflects across the origin way down here to negative 2, negative 8. Okay, so now here are the rules. And sorry if it's a little bit fuzzy. This is equivalent. It's pretty much equivalent to what the book has. So given an equation in x and y, okay, so what do we do? Okay, if we replace x with negative x, okay, so anytime in the equation, if you see x, change it to negative x. If you get an equivalent expression, okay, then you have something called y-axis symmetry. So you just change x to negative x, and you say, hey, I get the same thing back. That's called y-axis symmetry. And here's an example. For y equals x squared, right? If I change this to negative x, y equals negative x squared, and then you say to yourself, oh, negative x squared is the same as x squared, right? So you get the same thing back, okay? So replacing x with negative x gives you the same equation back. Then you have something called y-axis symmetry. Now, reverse it with y. If you replace y with negative y, and you get the equivalent equation, you have x-axis symmetry, okay? So in the original equation, change y to negative y, like here, right? X equals y squared, make it x equals parentheses negative y squared, but you notice that is the same thing as just y squared. Okay? So that's something called x-axis symmetry. You have x-axis symmetry. Okay, then I'm going to go up. Sorry, because of time, I have to keep up with what I have. Okay, now, for origin symmetry, you do both. Replace x with negative x and y with negative y. And if you get an equivalent equation, you have something called origin symmetry. So change x to negative x, y to negative y, and you get an equivalent equation. So an example was y equals x cubed. So I mentioned back over here, y equals x cubed had origin symmetry. So replace x with negative x, replace y with negative y, okay? And if you do that, you have negative y equals, what is negative x cubed? Negative x times negative x is negative x cubed, but that is equivalent to the original. If I just multiply both sides by -1, you get y equals x cubed. So yes, indeed, you do have something called origin symmetry in this particular case. And I'll show you how to do some of those. Okay, so a quick recap of my version. My version is not better than the book's version, it's equivalent. Okay, if you replace x with negative x, and you get the same equation back, you have y-axis symmetry. If you replace y with negative y, and you get the same thing back, you have x-axis symmetry. If you do both, replace x with negative x and y with negative y, you get an equivalent equation. You have so-called origin symmetry. You may write all of this on your cheat sheet for the test. Okay, and sorry, because of time, I have to keep going. You've got this in the video, but I'm going to get started with some of the problems. Okay, we had 1 through 8 all, A-L-L. Okay, now the back of the book gives you odd answers. You don't have any evens, so I'll try to show you at least the evens. Okay, so on page 28, they just show you some graphs and it asks you what kind of symmetry does it exhibit. Okay, so let me do the evens, 2, 4, 6, and 8. Okay, 2, so does it exhibit x-axis symmetry? Okay, you see, how do you know? So if you imagine you put a mirror right here, x-axis, right? Is the top the mirror image of the bottom? No, it isn't. Right? So you do not have x-axis symmetry. And it looks like you do not have y-axis symmetry either. Okay, so does that y-axis act as a mirror? Is the reflection of the left side the same as the right side? No, right? Because over here, if the reflection were true, you'd have to have something over here, right? And you'd have to have something over here, but you don't. So you don't have that. So you don't have either x or y-axis symmetry. It does look like you have origin symmetry. So the answer to number 2 is that you have origin symmetry. So just put down origin symmetry for number 2. By the way, you can abbreviate symmetry with SYM on the homework or quiz or test. If you just want to put SYM, I know it means symmetry. Okay? So if I take a point and reflect across the origin, or this point reflects across to here, or this point reflects across to here. So we have origin symmetry. Okay. Now, number 4, what symmetry does it exhibit? Okay, so let's check. X-axis? No. The top is not the reflection of the bottom. Y-axis, is the top the reflection of the bottom? No, it is not. Right? That means the left side should be a mirror image of the right side. It isn't. And it doesn't look like I have any origin symmetry either. Okay. And a good way to show that is this point here, right, should reflect to something over here. And this point should reflect to something over here, but we don't have it. So number 4 has no symmetry. So for number 4, just put down no symmetry or no sim, S-Y-M. Okay, sorry for the yellow. I don't know why it does that. I can't control it. Okay, I think you can still see it though. Okay, 6. 6 does have some symmetry. Can you guess the symmetry for 6? It's a parabola which opens down. It has only y-axis symmetry, right? So if I put a mirror right on the y-axis, the left side is a reflection of the right side. Is that right? Okay. It does not have x-axis symmetry. Clearly, if I put a line on the x-axis, the top is not match the bottom. I do not have origin symmetry, for if I reflect across the origin, right, then there should be a point over here, but there isn't. Okay, so it only has y-axis symmetry. Okay, and then how about number 8? Can you see what kind of symmetry 8 has? It does have a symmetry. Can you guess which one? Okay, the answer for 8 is that it has origin symmetry. Origin symmetry. It does not have y-axis or x-axis, but 8 has origin symmetry. You can write origin S-Y-M. Okay, so it looks like a point here reflects across here, a point here reflects across here, and so on. Okay. All right, so that's that. I'll go ahead and I'll do some odd ones. Okay, look at 3, the circle. Now you know and I know that circles are nice and round and lots of symmetry with respect to it. Okay, so think about number 3. What would you answer for this? Okay, does it have x-axis symmetry, y-axis symmetry, origin symmetry? Okay, number 3 has all 3 of them. Number 3 has x-axis, y-axis, and origin symmetry. Maybe for now, if you want to just write something quick, just put all, or all S-Y-M. Okay, has all symmetry. And by the way, if I ask you something like that in a quiz or test, if you just want to put down all symmetries, that's fine. Okay, so it's symmetric with respect to the x-axis. The top is a reflection of the bottom. It has y-axis symmetry. The left and the right are mirror images of each other. And origin symmetry. If I take a point here and reflect across the origin, or a point over here has another point over here, or a point over here has a point over here. So it has all symmetries. Okay. All right. Okay, now I'll talk about these. Determine any axis intercepts and describe any axis or origin symmetry. Okay, so you have a lot of problems that are here like that. So I'll show you some of those. So find any intercepts. I'll show you how to do that, and determine any symmetry. Okay, so problem 9, y equals x plus 3. Okay, and by the way, you don't have to graph these, but I ended up graphing it anyway, just so I can show you what it's about. Okay, it asks for intercepts. Okay, you might recall for the intercepts, you just plug in the zeros. Okay, x-intercept means y equals 0. y-intercept means x equals 0. Okay, so if you've forgotten that, you can put that in your cheat sheet. Okay, put x-intercept means plug in y equals 0. Y-intercept means plug in x equals 0. Quick timeout. Okay, this is the x-axis, right? If you look at the x-axis, every point that I'm picking on the x-axis, the y is equal to 0. Do you agree? And likewise for a y-intercept. Okay, look at the y-intercept. Every point here, x is equal to 0. Okay, so I plug in y is 0, put a 0 right here, then x has to be -3. Algebra is easy, right? 0 equals x plus 3, so x is -3. And likewise for y-intercept, plug in x is 0. If you put a 0 right there, that means y is 3. Okay, now they're asking us to check for symmetry. So check for symmetry, I do all this stuff here. Replace x with -x, replace y with -y, and then do both. So here we go. So this was the original, right? Replace x with -x, y equals -x plus 3. Okay, is that equivalent to the original? No, it isn't. So that means you do not have y-axis symmetry. We do not have y-axis symmetry. Now I replace y with -y. So right here, put -y, it looks like this, right? Is this equivalent to this? No way, of course not, right? You change y to -y. They're not equivalent, so you do not have x-axis symmetry. So no x-axis symmetry, no y-axis symmetry. And now you do both. Replace x with -x and y with -y. That means back in the original, put -y here, put -x here. So -y equals -x plus 3. Is this equivalent to the original? The answer is still no. You might say, what did I multiply both sides by -1? If I multiply both sides by -1, that would be y, that would be x, but this would change to -3, right? And that's not the same as this. So they're not equivalent. So none of them are equivalent. So you end up with no symmetry. Okay, so the answer to this is no symmetry. Okay, so the problem's finished, but I'm going to dig a little bit deeper. Y equals x plus 3, that's a line, right? Y equals mx plus b, slope of 1, y-intercept of 3. Very crudely, it has this graph. Okay, so it is not symmetric with respect to the y-axis, right? That doesn't give me a mirror image. It's not symmetric with respect to the x-axis. There's no mirror image there. And there's no symmetry with respect to the origin, because this point here should give me another one reflected across the origin down here. It does not. So that's that. Okay. All right, I was going to show you 15 now. 15, y equals 1 minus x squared. All right, so x-intercept, remember x-intercept means y equals 0. Y-intercept means x equals 0. And by the way, if you feel better, this entire example 9, you can put that whole thing on your cheat sheet. Now, I am limiting you to 8.5 by 11, so you kind of have to pick and choose. I mean, if you literally put everything down, you wouldn't have enough space for 8.5 by 11, right? So when it comes to the test, you have to decide for yourself, okay, I know how to do that, so I don't need to write that down. But maybe you say, I'm a little bit iffy on this, so I better write this whole example down on my cheat sheet. You're allowed to do that. Okay, but you're clearly not going to be able to put everything down. So you have to pick and choose when it comes to the test. I'll put this thing down. Oh, I think I got that one down, Pat. I don't need to put that down, and so forth, okay? All right, let y equal 0. Put a 0 here. Okay. That means x is going to be plus or minus 1. All right, 1 minus x squared equals 0. X can be 1. X can be -1. So plus or minus 1, 0 are the x-intercepts. Y-intercept, plug in x is 0. That's easy. Put a 0 here. 1 minus 0 is 1. All right, so these are my intercepts. X-intercepts, plus or minus 1, 0, y-intercept 0, 1. All right, now I replace x with negative x. Okay, so replace x with negative x. So right here, instead of writing x, I put negative x. So it's 1 minus parentheses negative x squared. But what is negative x squared? It's the same as x squared. So I get back 1 minus x squared. That is equivalent to the original. So I have y-axis symmetry. I have symmetry with respect to the y-axis. Then according to protocol, replace y with negative y. So I replace y with negative y. So back in my original, put negative y. It looks like this. Negative y equals 1 minus x squared. Is this equivalent to this? No, no way. That had a y, that had a negative y. So I have no x-axis symmetry. And finally, I do both. So remember, for origin symmetry, you do both of them. So replace x with negative x and y with negative y. So in the original, change this to negative y, change this to negative x, and it ends up looking like this. Okay, so this y becomes this negative y. This negative x becomes parentheses negative x. Now, I know that negative x squared is the same as x squared. So I have negative y equals 1 minus x squared. But is that equivalent to the original? The answer is no. This whole thing is not the same as this because it has an extra negative. So you do not have origin symmetry. Okay, so the problem's finished. Okay, that's it, but I'll just dig a little bit deeper. Okay, if you were to graph that, you might recall that this is a parabola opening down. Okay, it ends up looking something like this. If you were to plot some points, it looks like this. Okay, so intercepts 0, 1, plus or minus 1, 0. These two guys, right? That looks like negative 1, 0. This one is 1, 0. And like we anticipated, we do have y-axis symmetry. So I have symmetry with respect to the y-axis. I do not have symmetry with respect to the x-axis. I don't get a mirror image there. And you don't have origin symmetry. Otherwise, a point here would reflect to a point here, but I don't have that. Again, in general, for these problems, you don't have to graph it, but I graphed it just for teaching purposes. Okay, and I was going to show you one more, and maybe that's about it. Problem number 19, please. Problem 19 goes like this. X equals y squared minus 1. I won't bother to graph that. That's very similar to the previous problem. Okay. The only difference is that instead of the x squared, they have y squared. X equals y squared minus 1. Okay, x-intercept. Plug in y equals 0. Put a 0 there. I get x equals negative 1. So negative 1, 0. Okay, y-intercept means plug in x is 0. If you put a 0 here, you get 0 equals y squared minus 1. You can solve that by factoring or by the square root property. Y is plus or minus 1. Okay. 1 is easy, but sometimes people forget negative 1. Negative 1 also works. So 0, comma, plus or minus 1. So those are my intercepts. Okay, so now I replace x with negative x. So right here, change it to negative x. It looks like this, right? And is this whole equation equivalent to this whole equation? No, it is not. So I do not have y-axis symmetry. Now I replace y with negative y. So right here, change it to parentheses negative y. So x equals negative y squared minus 1. But negative y squared is the same as y squared. So I can have x equals y squared minus 1. That is equivalent to the original. So by our rule, I have x-axis symmetry. Okay. So x-axis symmetry. And then I do both. Replace x with negative x and y with negative y. So right here, change this to negative x, change this to negative y. So it looks like this. Negative x equals parentheses negative y squared minus 1. Now again, negative y squared is the same as y squared. So I have negative x equals y squared minus 1. So is this whole equation equivalent to the original? No, it is not, because I have an extra negative on the x. So I do not have origin symmetry. So that's the answer for that one. Okay, we have 8 minutes. I have time for one more. Sorry, I can get one more in. If I can get one more, then I might as well, and then I'll stop, I think, after that one. Okay, number 23, please. 23. Y equals negative x cubed. Y equals negative x cubed. Okay, for this one, I'll do what I normally do, but I'm going to digress. This is the graph. If you were to graph negative x cubed, it looks like this. Okay, maybe just ask yourself, do you see what symmetry this might have? This graph right here. It has origin symmetry. It does not have symmetry with respect to the x-axis. Okay, I don't get a mirror image, nor the y-axis, but I do have origin symmetry. A point here seems to bounce off over here, and a point here bounces over there, and so on. Okay, so anyway, how do you work it out? Well, by the way, for intercepts, it's 0, 0, right? The only intercept is 0, 0, which is borne out by the picture. Okay, replace x with negative x. So right here, change this to parentheses negative x. So negative x cubed, negative x times negative x times negative x is negative x, but there's a negative in front of the whole thing. So the right-hand side now becomes positive x cubed. So the new equation is y equals x cubed. Is that the same as the original? No, it isn't, because there's a minus here. So no y-axis symmetry. Okay, replace y with negative y. So right here, change it to that, negative y. So I have negative y equals negative x cubed. Well, if you multiply both sides by negative 1, that's normally the trick when you have something like that. You get y equals x cubed. But once again, that's not the same as this, not equivalent to this. So I do not have x-axis symmetry. But in this case, if I do both, if I replace x with negative x and y with negative y, so change that to negative y. There it is. The 2 pens illustrate that. If I change this to parentheses negative x, this pen to this pen, I now have this. Negative y equals negative parentheses negative x cubed. Okay. Now, the whole right-hand side is x cubed, because we said already negative x times negative x times negative x is negative x cubed, but the negative in front of the whole thing makes it a positive y cubed. Okay. And now, is this equivalent to this? Actually, it is, because if you now multiply both sides by negative 1, right? Multiply both sides here by negative 1, it does look like this, y equals negative x cubed. So I do get an equivalent expression. So I do have origin symmetry. All right, so final answer for that one. The only intercept is the origin, so that's x-intercept and y-intercept. 0, 0, when you plug in 0, you get 0. And I have origin symmetry for that one. Okay, and that'll do it for the lecture formally. So let me stop the share and turn off the recording.